We're back. All right. This week, we're wrapping up the acid-base unit. Finally, seems like it's been forever. All right, we're going to wrap it up by doing three things. We'll start out by doing buffer solutions. All right, what are buffer solutions? How do they work? Then we'll do titrations. Titrations, you're going to have a lab this week, and it's on a titration. Oh, you're going to do a lab. That's right, you are. But we're not in school. Still doing a lab. All right, now the titration lab. And then we'll wrap this up with what's called solubility of a salt when you switch with pH. So if you take a salt and add it to acid or add to a base versus water, how does that change things around? To wrap up, finally, the acid-base unit. All right, now I know you all have watched. You've all watched the video on buffers. It was a short video. It was a good explanation. Okay, I don't have to reinvent the wheel. I don't have to, there's a good buffer of the solution thing out there, and I had you watch. It's only 3 minutes, so just go watch it. Okay, so now we all know what a buffer is. Good. We're ready to start on our problems of El Weeko. Okay, first question on our problem says, which of the following solutions can act as a buffer? Now, we all know from the video that buffers will neutralize, to a degree, they will neutralize any acid or any base added to a solution. You are a buffer. You are a biological buffer, and it's a darn good thing you are. Your blood is a pH of 7.4. It has to stay there. If it doesn't, then it will not be able to transport oxygen and carbon dioxide throughout the bloodstream, and you will go, Astro. That would be a bad day for you. So you want to make sure that your blood pH maintains 7.4. And how does that happen? Well, that's because your blood has a weak acid floating around in it, and that's carbonic acid. And so, what did I just say? Weak acid. Yes, a buffer solution must have a weak acid. It can be a weak base, but that's much less common. But a weak acid or a weak base, that's what you have to have for a buffer solution. And you have to have its conjugate salt. Conjugate salt. We've done these. We have. Not last week, but the week before. The last thing we covered was common ion effect. What happens if you throw a salt with a common ion to the weak acid? What happens to the pH? What happens to the system? We didn't call it a buffer system, but that's a buffer system. So let me show you. Let me give you an example. We'll give you an example. Let's just dive into the questions. All right, here we go. Question number 1 says, which one of the following combinations would make a buffer? Okay, take a look at the first one. First one says KCN and HCN. Well, which one of those is the acid? You'd better know this. HCN, very good. It's got the H. Okay, that's your acid. It's a weak acid, too. We know it's weak because it's not one of the strong ones. So HCN is weak. HCN being weak, here will go both ways, breaks down hydrogen and cyanide. So we got hydrogen in the cyanide ion. Now, if we happen to throw in a salt that has the negative ion on it, in this case I just said KCN, it didn't have to be KCN, it could have been NaCN or MgCN2, it could have been anything in front, any positive ion. The key is the negative ion, because the negative ion is common in this reaction. Hence the common ion effect, which we had gone over before. Again, we didn't call those buffers, but they were. So here's why. If we have some salt thrown in here, in this case I put KCN, well, the K doesn't do anything. The K, when it goes into water, it dissolves, very soluble. So this dissolves. The K just kind of hangs around. It's not part of the reaction, so who cares? But this is in there. And usually you already have this floating around in the solution. So you have the weak acid and what's called its conjugate base. All right, so it came from the salt that was added, the conjugate salt, which was added to the solution. And so now you have some of this already there. You have this and you have this. Okay, so how does this act as a buffer? How could this help us with pH? Okay, well, what happened if we end up taking some, well, let's say this is, you drink things which are acidic all the time. Orange juice, coffee, cranberry juice, pomegranate juice. Whatever you want to drink, Many things we consume are acidic, and that can, if that gets into our system, your blood can go blah and freak out and drop, lower the pH and dead. No, but it doesn't, because you have a buffer in your blood which deals with those possible pH changes or extra hydrogens which are being thrown into your system. Or if you decide to eat soap like Ralphie on the Red Ryder BB gun movie, Lifebuoy, okay? No, that's a base, and so buffers can handle those as well. Here's how, very simple. If you add some hydrogen to this now, throw some acid in it, add some hydrogen in, what happens? That's going to grab it. That you add some hydrogen, this grabs that hydrogen, sucks it right out, right out of the solution. It forms some of our weak, this weak acid. So we get rid of that bit hydrogen by adding to the CN ion. What if we have a base added where we throw some hydroxide in? Well, the hydroxide will be, boom, consumed by the weak acid. The weak acid will take some of those hydrogens and say, here, take those and get rid of that, make water out of it, and deal with the base. Hydroxide dealt with here, hydrogens dealt with here. You add any hydrogens or any hydroxides, this system, this solution can deal with it. Now, of course, if you add a crap ton, and we all know a crap ton's a lot, it's the international system unit for 100,000. Crap, it'd be 100,000 tons, crap ton. If you add that much acid or base, you might overwhelm the buffer solution. I mean, it'd be kind of like if you were to take a gallon of hydrochloric acid, do not try this at home, for professionals only, okay, and drink concentrated hydrochloric acid. It's going to be a very bad experience for multiple reasons. You will die. Again, trust me on this one, you will, okay? And the reason is because you're overwhelming your natural buffer system. The buffer system can't handle that much H, but it can handle some of the H you throw into your system and deal and keep the pH the same. Okay. So out of these, first four, 1, 2, 3, the first three, those are good buffer systems. Why? Because you have a weak acid or a weak base and a salt that has a common ion in it. Those are buffers. The last one, not a buffer, not going to work. Well, let's see if you can figure out why. We have HI. All right, that's the one of the strong acids that you know is strong. And this breaks down 100%, so we have the arrow going in one direction. So you can take anything you want, any common salt here, conjugate salt. We have sodium iodide. Throw some of that in, sure. So throw some sodium iodide in there. This comes out. This is gone. This goes away because it's not in the reaction, so who cares? So this says, hey, look, we're adding some of this iodine in. Deal with it, man. Deal with it. Well, actually, that's not the deal with it. But we have some extra iodine waiting around here, waiting to deal with it. Dealing with it would be actually some hydrogen in. You throw some hydrogen in, and this says, I will deal with you. I will deal with you. Nah, no, you won't. Because you might go, yes, I will. I will take this and I will grab you and I'll make it go in this direction and get rid of you. No, you can see the arrow goes one way. It's a strong acid. That would be a strong acid. It dissociates. It can't stick together. So it won't be able to go back and get rid of the extra hydrogens you put in. So a strong acid or a strong base will not work as a buffer. Okay. Now let's do some problem solving, because we love problem solving. So in the first problem, we're done with that one. We know the last one could not work as a buffer system because you have a strong acid. No. Definition. And I was trying to show you here why, and we'll see why again as we keep going these problems. You got to have a weak acid, weak base, and it's a conjugate salt, a salt with a common ion to the acid or base. Moving on. Problem 2. Calculate the pH of the following 2 buffer solutions. So these are buffer solutions. Let's calculate their pH. All right. So we have A, 2 molar sodium acetate and 2 molar. Remember what that acid is? Yes, it is. It's weak. Acetic acid. Very good. Very good, Johnny. Okay. So acetic acid weak. So we'll draw this out. Oh man, I mean that's need some room here. So CH3COO negative plus hydrogen. Okay. So there's our weak acid base in its equilibrium state, but we've added, because it says right here that we've added some salt to it. That's how come it's a buffer, salt and weak. And it happens to be sodium acid. But again, it doesn't matter what that sodium is. It doesn't matter. The thing is, we've added some of the acetate ion. So some of the acetate ion is already hanging out. So some of the acetate ion is already here. It's already ready, already there. How much? How much of these do we have? 2 molar. Ice chart time. Oh, I love ice charts. Initially, I have 2 molar of my weak acid. And here I have 2 molar of the acetate ion. We got that from adding the salt in. Okay, that's where the 2 molar came from. And at this point, this established equilibrium. I don't have any of this yet. So let's do what we've been doing for weeks. Let's figure out what the pH of this is. So change negative X, positive X, positive X. 2 minus X, 2 plus X, X. All right, K. Now, the K for acetic acid is 1.8 times 10 to the negative fifth, if I remember right, and I think I do. So that K, remember, I'm not going to write the K, how to do K, as we've done that. So let's just assume that you know how to write K values. So K, 1.8 times 10 to the negative fifth equals products over reactants. So 2 plus X, X, 2 minus X. Okay, what do we know? We know that we can do the rule of 100. Take 2, divide it by that, and you get a very large number, bigger than 100. That means that these are small and can go away. And look at the magic. Look how easy this math is. Those 2's also cancel. Those are gone. So the only thing you're left with is the K value for the acid, the Ka. So that X is equal to 1.8 times 10 to the negative fifth. And what is that X? That's the hydrogen ion concentration, and it did want to know what the pH is. So I need to know the hydrogen ion concentration. So we're going to take this value for hydrogen and put that in to our negative log concentration of the hydrogen, 1.8 times 10 to the negative 5. All right, we do the math on that. And that comes out to be 4.7, yes, 4.74. 4.74 is my pH for this ready to go buffer solution. It's just ready to go. Now, if you were to add some hydrogens to it, you would get rid of those by moving those hydrogens to the left. If you add some hydroxide, OH, some H's will come off of this and throw those in that direction. We're ready to rock. This solution is ready to go. So you switch with this system, it's going to be able to handle it. All right, now the next question, part B of this question here, is what if we have the same system? We have the acetic acid and the sodium acetate, but 0.2 molar concentration this time instead of 2. This is quick. Here's why. 0.2. 0.2. 0.2. 0.2. And if we go back into the math we just did, these are going to be on top. So 0.2 plus X times X, 0.2 minus X. I mean, some of you already know. You know what's going to happen. Same thing as last time. These X's are small. The 2's cancel. In this case, 0.2. 0.2's cancel. So I'm left with X. It's the same X value we had before. We would have a pH of 4.74. So because we changed the concentrations, we made 1/10 the strength in the second case. In the first case, the pH is still the same. That didn't change. But there's another question to this. It says, which of these two buffer solutions, the one with the 2 molar concentration or the one with the 0.2 molar concentration, would be a better buffer solution, and why? That's right, you know, the one with the 2 molar concentration is more concentrated. Well, Janie over there saying, well, so what? So what difference does that make? It matters because remember what these buffers are they're ready to do. They're ready to handle any extra hydrogens or hydroxides you put into them. So if you have a higher concentration solution, that has more buffer. More buffer means it can handle more H's or OH's they could put into the solution before they get used up. And they will get used up. We'll demonstrate that with some problem solving soon. But if you are adding H's and OH's to this, if you have higher concentrations, they can handle more hydrogens that get thrown into the system or hydroxides with keeping that pH right about where it is. They will run out. I mean, they'll last forever. If you keep adding stuff to the system, they'll keep dealing with it, but eventually you'll run out of the good guys and they get overwhelmed. So more concentration, you can do the job for a longer period of time. Okay, whew. Okay, this is already like 16 minutes, which means it's going to take me like 16 hours to upload this stupid thing. So I'm going to stop here on this one. And